The mission of IEEE students is to deliver a common, high-quality IEEE student membership experience globally for lifelong professional membership through IEEE.
IEEE is a family. The friends you build through volunteering stay there. You really make friends for life.
Getting involved at your local student branch, your local section, and your larger region is one of the many benefits that IEEE students have. You could also apply for a variety of awards, both as an individual and as an IEEE student member of your local branch. You can also get involved in a variety of contests and competitions, including our #1 student competition, IEEE Extreme, a 24-hour global coding competition with over 8,000 students involved annually. IEEE Potentials is a premier student magazine. It provides you with the opportunity to get published and to review your peers' work as well. With over 400,000 members in the IEEE Global Network, you can get connected, find a mentor, and also collaborate with professionals in your field.
If you want to do something to impact your community through IEEE, it gives you the resources.
You can make the most of your IEEE membership by completing your profile. It allows us to contact you and keep you up to date with what's happening at the global IEEE offices. Take advantage of being an IEEE student member by
C'est bon, hein? Oui, c'est bon, je pense. Mais après, c'est beau, ils sont. Il faut leur envoyer un.
7, c'est ça. Ah oui, 7. Ah oui.
Ah, il y en a un sur la Cabbia.
Le 4, il ça disparaît.
Après, l'audio devrait sortir.
Ils vont pas laisser mon frère streamer comme toi. In the show.
Il y a les autres qui sont là ou pas?
Je ne vois pas les sons.
Hop. Ben,
Mais les autres sont
voilà.
Le problème, c'est qu'il faut que les autres
mettre leur.
mettre leur caméra.
Ok, on peut mettre dans le chat, est-ce qu'ils peuvent réactiver leur caméra? Christophe,
Oui.
Cédric et Marc.
Ouais, je vais écrire. Oui, il faut activer
Voilà.
la caméra.
Est-ce que c'est bon?
Merci.
Merci beaucoup, Andrés. Allez, bonne manip.
Et l'audio? L'audio, c'est bon? Ça sort d'ici? Ah, ok. Ok. Ça me va.
Ok, c'est tu commences.
On commence? C'est bon?
Oui, normal. Le président qui donnera la parole.
Ouais, c'est,
Can,
It's okay?
can you hear me?
Yeah, very well.
Yeah, I can see you, but
Can you hear me?
apparently you can hear me, but I can hear you. So, il faut. Ça devrait sortir de là, c'est tout connecté en fait.
Hello, can you hear me now? Marco, can you hear me now? Hello?
T'as choisi.
C'est lui qui est dans le backstage, le responsable. Alina, c'est lui qui est dans le backstage, il ne peut pas rentrer.
Il peut pas rentrer?
Il a écrit ça.
Could you please try to talk?
Yeah, can you hear me now?
Yeah.
Hello?
Est-ce que tout le monde peut parler?
Can everybody try and speak? Right now, all the other members will be coming.
Christophe, can you speak, please?
Yeah, marqué is muted.
Oui, le mien.
Ah, c'est bien. Ah, ok.
Christophe, can you speak, please?
C'est qui qu'on entendait là?
So Marco is talking.
Can you hear me?
Yeah, I can hear you, but
Okay.
I can hear you. I can see the other.
So Christophe, it doesn't.
Christoph just wrote in the chat, I speak, but I don't. Yeah.
Hello? Hello, Shandan.
Yeah, hi.
I can hear.
I can hear you also.
I will answer for the questions. Yeah. And Cedric?
Cedric,
Is Cedric Durand in the studio?
Non,
Cédric Durand, il est là ou pas?
je crois pas.
Cédric Durand.
Still the backstage.
Ah, Cedric Durand is in the backstage.
Okay, yeah.
Ah, là, il apparaît là. Ah.
Backstage, stage. Don't say hello.
Ah, attends, Christophe. Ouais, Christophe.
Ouais, Philippe, bon, je vous entends très très bien. L'écran, je le vois parfaitement. Donc après, je me démerderai avec, je t'appellerai ou je sais pas, pour les questions, on se démerdera. Ah bon?
Ouais,
Ah bon, ouais.
Ok. Mais si ça marche pas, tu nous appelles comme ça on t'entend.
Ok. On fera ça. Donc vous m'entendez là?
Oui, parfait, oui.
Ah ben, magnifique alors. Il a fallu que j'appelle par téléphone pour faire le lien.
et Cédric,
Bon, on attend encore Cédric.
D'accord.
Sinon, pour les autres, ça marche. Et puis,
oh,
I will not activate my camera because I'm not sure of the bandwidth I have, so I prefer to have a good quality of sound and not video.
Marina, est-ce que tu as peut-être son téléphone hein, pour l'appeler, pour voir s'il est bloqué quelque part? Oui. Je sais pas, parce que... Il a peut-être un problème avec son PC, ça complique.
il a répondu tout à l'heure.
Parce qu'ils travaillent tous, restés avec Teams tout le temps, hein, ils sont tous à
Oui, mais là, c'est strict. Oui, oui, mais peut-être qu'avec StreamYard, il y a des...
Mais c'est ça. Ah ouais.
Peut-être qu'il a... Des fois, il y a des trucs, tu sais pas pourquoi, ça décide de bugger.
Ça arrive à développer. Ils sont fixes à ST, moi.
Ça dépend des bâtiments. Ça dépend aussi, il y a certains logiciels qui passent pas en fonction. Il est chez lui, là, il est chez lui. Quand c'est dans les bâtiments, des fois, ça a des sécurités.
Ouais, si, parce que ils sont fixes. Ouais, attends, il n'est pas possible. Je crois que c'est Marina, elle appelle. Ah si, on sait, oui. Marina, elle appelle. Il n'est pas là.
Quartier Somia,
Ah, peut-être sur YouTube.
je vais leur écrire.
Normalement, je crois que c'est dans son message, il y a marqué que c'était interdit
Ah, oui, c'est vrai.
Peut-être qu'elle a appliqué le truc à la règle.
Ouais.
Voilà.
Et ils sont à Paris.
Ouais,
Ils sont en haut.
je sais pas. Je leur ai écrit.
Juste appliquer les règles.
C'est possible.
Comme il a mis dans son mail que ce ne serait pas.
Ouais.
Il n'y aurait personne dans l'amphi.
Ouais, c'est ça.
Il y aurait un truc.
Ah, c'est le serveur resté peut-être.
S'il a testé.
Voilà, il suffit de pour les visuels.
S'il est ST, c'est très bien.
Ça passera pas. Peut-être il a un ordi perso.
Hein?
Il a peut-être un ordi perso.
Tu rentres pas avec un ordi perso ST. Pas avec n'importe quoi.
Ouais.
Ouais, c'est un peu tout court. Là.
Hein?
C'est un peu tout court en ce moment. C'est vrai qu'il n'a pas remis les PhD depuis.
Ouais. C'est trop long, ça.
Tu l'as dit à Christine?
Oui. C'est un message à quartier.
C'est la connexion ST qui bloque.
Ah,
Donc, il va faire avec son PC perso.
ah voilà. Ah.
Ah oui, il est chez lui quand même.
Parce qu'il est dans le télétravail, donc il va se reconnecter avec son PC.
La configuration qui est protégée.
Ouais, c'est ça. J'avais pas pensé à.
La présidence, il voit sur YouTube, il peut suivre sur YouTube et faire des questions par téléphone.
The mission of IEEE students is to deliver a common, high-quality IEEE student membership experience globally for lifelong professional membership through IEEE.
IEEE is a family. The friends you build through volunteering stay there. You really make friends for life.
Getting involved at your local student branch, your local section, and your larger region is one of the many benefits that IEEE students have. You could also apply for a variety of awards, both as an individual and as an IEEE student member of your local branch. You can also get involved in a variety of contests and competitions, including our #1 student competition, IEEE Extreme, a 24-hour global coding competition with over 8,000 students involved annually. IEEE Potentials is a premier student magazine. It provides you with the opportunity to get published and to review your peers' work as well. With over 400,000 members in the IEEE Global Network, you can get connected, find a mentor, and also collaborate with professionals in your field.
If you want to do something to impact your community through IEEE, it gives you the resources.
You can make the most of your IEEE membership by completing your profile. It allows us to contact you and keep you up to date with what's happening at the global IEEE offices. Take advantage of being an IEEE student member by collaborating on projects within your local student branch and your section with professional members. By collaborating on projects, you have the opportunity to get featured on IEEE TV. We'll see you there.
EPICS and IEEE empower students and local communities around the world to apply engineering to solve those challenges.
The IEEE Event Finder allows you to locate conferences, meetings, events, and activities in your area and worldwide. You can get involved in a variety of special interest groups as well. Women in Engineering, Standards, and IEEE Young Professionals.
YP represent!
Of course, that's when you graduate. Remember, IEEE prides itself on being your professional home. Be sure to take advantage of everything the IEEE has to offer.
The more you put in, the more you get out.
We share the same fears, we share the same hopes, we share the same visions, and this is the best place we can exchange our experience, and at the same time we can get support from our experienced colleagues at the same time. It's perfect.
Je pense que vous avez testé le PC de chacun.
De quoi?
Vous n'avez pas testé le PC de chacun?
Non.
Par contre, tu peux remettre, Cédric, Et tu peux parler?
Là, je crois que ça arrive, là, regarde, on voit ça, on voit qu'il...
Oh, alors, on va
La puissance, tu vois, tu sens qu'il y a des deux. Ouais, il y a des fois, tu peux un petit peu ça. Et ça s'est joué, tu vois, c'est bon, tu vois. Du coup, il regarde les séries de sel. Il regarde il essaie de trouver un cadre qui ressemble à le coup, elle est encore sortie, du coup, encore une date fictive. C'est important, bien sûr.
Ah non, ça marche pas. Non,
Pareil,
Ouais. Ah, c'est un choc.
on va sur un truc, je crois.
Ouais, par contre, il n'y a plus d'Excel.
Ok.
Du coup, Pierre Jour, il regarde sur des calls un peu semblables. Apparemment, il y aura des choses qui doivent leur parler du février. Là. Il se réunissent régulièrement au bord de. Je dis ça. On va parler parce qu'on va faire le projet de dissimulation avec Andrea pour être là. Ouais. Là, il est pas assez fort.
Si je devais résumer la Bibranche avec vous aujourd'hui, je dirais que c'est d'abord des rencontres. Des rencontres entre étudiants appartenant à différents laboratoires, différentes entreprises, mais aussi avec des chercheurs venant du monde entier. Nous accueillons tous les étudiants appartenant au domaine de l'électronique, au sens large. Nous donnons la possibilité à ces étudiants membres de créer leur réseau professionnel dans des domaines qui leur tiennent à cœur. Être membre Bibranche, et donc membre I3E par extension, cela vous donne beaucoup d'avantages. Notamment, vous aurez accès à une grande librairie d'articles de conférences en électronique, mais aussi à l'actualité des dernières technologies et aux événements organisés par les entreprises de pointe. Mais avant tout, cela vous permet de faire partie d'une des plus grandes communautés scientifiques mondiales. Et tout cela pour seulement $20. Sur le campus bordelais, on organise des événements à peu près tous les mois, sur place ou sous forme de virtual event, au cours desquels on a des invités tels que des chercheurs. Mais on permet aussi aux étudiants du campus bordelais de transformer leur projet d'études en projet I3E, en ayant un soutien financier, et nous les accompagnons aussi dans l'écriture d'articles scientifiques afin qu'ils aillent en conférence par la suite.
Être à la Bibranche, c'est faire partie d'une équipe dynamique et soudée pour promouvoir la science.
Pour moi, la Bibranche, c'est l'occasion et l'opportunité de changer son quotidien d'étudiant. C'est l'occasion d'organiser tout plein de choses, des séminaires, des journées thématiques ou encore des concours technologiques autour de divers sujets scientifiques.
Rejoins la Bibranche.
La Bibranche.
Donc rejoignez tous la Bibranche.
Únete a la Bibranche.
It's a Bibranche, bye.
Unisciti alla Bibranche.
Une bonne blague pour la communauté. Ça, c'est plutôt bien.
definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you...
Hello.
La commande est partie avant hier, de regarder pour lequel il est arrivé. On commence la production.
Oui, unmute. Hello, Cedric speaking. Can you hear me?
Yeah, I can hear you. Can you hear me?
Yeah. So.
Can you?
Yeah, I can hear you.
Okay, great. Perfect. I can see you too. Perfect.
Désolé, j'ai eu plein de soucis pour me connecter.
Pas de souci. Okay. So we can start the test. So Marco will have more or less 45 minutes to present your work entitled Sub-millimeter wave on wafer calibration and device characterization. Please, Marco.
Thank you, Mr. Chairman, and for attending here today this presentation, and thank to all the committee members for joining us remotely. Sorry for the delay. I am today defending my dissertation on sub-millimeter wave on wafer calibration and device characterization. So first, there will be an introduction with the general overview of the state of the art, the motivation, and the main concepts of measurement, calibration, and the simulation setup. Second part will be dedicated to benchmarking TRL and SOLS calibration up to 500 gigahertz. Plus, two layouts that we have implemented will be directly compared to evaluate the high frequency performance. And on the third part, we will introduce two innovative structures, cal kits, for cal kits, which are meander lines and TRL and M3 TRL. And finally, conclusions will be drawn and a glimpse to upcoming works will be given. So, millimeter and sub-millimeter waves cover the region of the spectrum from microwave to optical frequencies, which is the so-called terahertz gap. These waves carry many of the benefits of both sides, because like radio waves, they can penetrate through a variety of non-conductive objects and walls. And like visible light, they have very short wavelengths, and which give very precise measurements and high-quality images. Nowadays, the trends for sub-millimeter electronics are no more just to fill the terahertz gap, but to do it in a meaningful way. And we see for this reason that the investigative thrust in this domain is leading to the design of compact systems and circuits, which allow applications in many fields, like the pharmaceutical sector, automotive, the cancer research, security, and so on. The RF technology that we use in this work is a bipolar CMOS implemented in the 55 nanometer node from ST Microelectronics. The choice of a CG by CMOS over other technologies for high frequency applications is due to the excellent RF performance of the CG HBT, joined to the low cost of manufacturing and the high level of integration of CMOS. The CG HBT that we use comes from a mature process that shows very good FT, Fmax performance. The goal of characterization is to provide to designers models with a reliable description of the device. And to do this, very accurate measurements have to be performed by retrieving the scattering parameters by a vector network analyzer, VNA, and removing all the contribution of the measuring system through calibration. And this is a cumbersome task to perform at high frequency. Above 110 gigahertz, in fact, we have to employ specific piece of equipment, and the back-end of line leaks remain a critical factor for a successful calibration. So classic S-parameter measurements for parameter extraction usually go up to 110, sometimes 220 gigahertz. They are often made with an on-wafer substrates, and however, they are unsuited for validation of compact models at submillimeter frequencies. Few research centers and groups extend their measurements up to the next band, which is the 220, 330 gigahertz band. But it is quite uncommon to have appropriate gear and simulation-backed results on these high-frequency bands for silicon technologies. We are going fully on wafer with S-parameter extraction up to 500 gigahertz. Every measurement that we'll make will be compared to a complete probe 3D electromagnetic simulation of both the cal kits and the transistor. And as I said, two novel calibration standard approaches will be proposed at the end of the presentation. At the IMS lab, we use two probe stations, which consist of two vector network analyzers with dedicated frequency extenders and probes for each of the measured bands. In this work, picoprobe probes from GGB will be used, as well as another set of infinity probe from form factor, which is formerly Cascade. They are all different in terms of shape, internal fabrication, and input connectors. So as mentioned, the contribution of the measuring system needs to be removed from raw measurements through calibration. The standard procedure is a two-step or two-tier calibration. And the goal is to set the imaginary reference plane, which is where the signal is supposed to be sent and received, as close as possible as to the intrinsic device under test. It is a common practice to perform the first step by measuring some reference standards, which is usually made of gold and located on a ceramic planar substrate, which we call a calibration substrate or impedance standard substrate, ISS. In practice, however, when resting the probes back on the silicon substrate when the device actually is, a different probe to substrate and probe to pad interaction will occur in the host medium. And for this reason, a calibration with standards lying on the same silicon substrate as the duty, which is an on-wafer calibration, is preferred. So the reference plane after the first step is now located on the pads or along the access lines. However, the parasitic contributions arise between and along the connection of the access line and the metal stack that goes down to the intrinsic device, which we call the back-end of line, BOL. They appear as resistances, inductances, and capacitances superimposed to the device characteristics, worsening its performance. We can model them all as lumped elements and remove them by using additional structures, which are called the de-embedding structures or dummies, to finally get to the DUT terminals. However, particular care at high frequency needs to be taken, as the signal waves are comparable or smaller than the back-end of line, and lump description of these parasitics may fall short. We associate the results on the measurements to a 3D electromagnetic simulation from HFSS. So 3 types of simulation have been carried out throughout these manuscripts. Intrinsic simulation represents the ideal behavior of the device under test with no contribution of the adjacent environment. However, probe simulation includes the RF pads and a model of the probe tip to evaluate the interaction with the environment. Picoprobe models have been designed to replicate the real setup for each of the measured bands. And finally, a hybrid solution has been developed to embed the compact model, the HiCAM compact model, to the HFSS environment to evaluate the effect of probes on the transistor size parameters. We added 2 exoports beneath the pins of our backend of line model and linked them to the HiCAM compact model, which describes the transistor's physics. So the main calibration algorithm that is used in this work is TRL. It employs at least 3 standards, and you can see them on the top on their implementation on run 2. They are a through, which is a direct connection between port 1 and port 2, a reflect, either open or short, and a line, which is a direct connection between ports, which delays the signal. Usually, like in this work, more than 1 line is needed because we want a broadband coverage of this method. TRL is constructed to measure traveling waves in transmission lines, and the reference plane after the calibration is set at the center of the through and can be moved in any desired position along the transmission line. To represent the parasitic contribution, we consider just a simple RLC network for which the short open deembedding routine is needed. So let's move to the second part, the calibration and layout benchmarking now. So our implemented on-wafer TRL cal kit is composed by an on-wafer through, either a pad open or a pad short that serve as reflects, and 2 lines to provide a validity of the algorithm from 20 to 500 gigahertz. The TRL sets the reference plane to be equal to the characteristic impedance of the design line, which maybe not always match exactly 50 ohm. So in order to correct it, we use a load implemented on the pad load standard, and we use the lumped load method from Dylan Williams and Roger Marks, which is needed to find the capacitance of the microstrip line. We implemented this method in our TRL cal kit to use interpolated values of the C line and the propagation constant gamma, extracted both by measured data. We also include the real part of gamma, which is alpha, and which have experienced that it modifies heavily the results on the transistors as parameters. Alpha is linked to the losses on the line, and we can see here how the inclusion of alpha changes one of the figures of merit of the transistor, which is the maximum oscillation frequency, Fmax. TRL is, of course, not the only existing algorithm for calibration, but is considered to be the most efficient and high frequency. In fact, it is not based on knowing ahead of the time the electrical behavior of the standards, which are expected to change due to parasitic effects. Rather, it is based on solving a problem that picks out the behavior of traveling waves in the transmission lines. So we compare it in the following with another algorithm, which is SALT, which stands for short, open, load, and through, and which is based on the idea that you already know what the reflection and transmission coefficients of the calibration standards are. So with additional calibration standards, you get one more condition on the VNA error terms. So enough standards will give enough conditions and will complete the error model. One of the main advantages of SALT over TRL is that it includes a crosstalk correction. So we can ask ourselves, up to which frequency band can the validity of SALT be extended without significant measurement accuracy loss? We will try to answer to the question, and for this analysis, off-wafer SALT is considered as well. We use a dedicated ISS for each band. The standards properties are all reported on datasheet for these standards for the off-wafer SALT. And these properties depend, of course, on the substrate, but also on the probes that are used. Then we use the standards on our calc kit for the on-wafer salt. We extract the on-wafer standards characteristics from on-wafer measurements that are performed. So here we can see the port capacitance of the pad open, C0, the port inductance of the pad short, L0, the delay of the through, and the load reactance, well, the load inductance, which is extracted by HFSS simulation. So here are the results of the comparison. We use the embedding structure, complete open, as a validation duty for calibration, and we observe the extracted capacitances. We see also the measured transit frequency FT as different bias points. Let me just point out that due to the different reference plane position between TRL and salt, an extra de-embedding step is included even for the passive validation. ISS is not shown above 220 gigahertz, since we have found diverging trends due to the excessive parasitics. So we can see that overall the quality of the on-wafer salt is good, and that means that the lumped standards are well suited to provide at least accurate or proper results up to high frequency. We can also notice the positive value of C12 decoupling capacitance all over the spectrum with the on-wafer salt. So in this part, we will compare two layout fabrications that have been designed subsequently, and they implement the same B55 backend of line. So eight copper layers plus the alu cap. They have been designed and they are evaluated in the following. We see a part of the floor plan here. One of the major design differences is that the ground thickness changes from 1.3 micron on run 2 to 0.17 micron on from run 1 to run 2, sorry. So in the first fabrication run 1, the structures are arranged in an aligned configuration and present what we call a silicon dioxide ring or oxide ring, which is nothing but a slot in copper surrounding each and every structure on the die. These elements, the presence of these elements could be non-intuitive, but it's simply a legacy of common layouts where dielectric usually separates all the structures. And it set them apart. Run 2 removes this element completely, and by using a single ground volume that connects all the pads to ground, plus a guard area behind the pads is created, which is aimed to better confine the electromagnetic field inside the DOT region. So these two elements, the ground volume plus this shielding region, form the so-called continuous ground plane. We also point out that for the run 2 structures are in a non-aligned position, in a staggered row position, that we call a chessboard configuration. This chessboard design increases the inline distance while reducing the structure's occupancy of the die, as we can see in the table here. So the continuous ground plane, as for it, it aims to reduce the modes propagating inside into the dielectric substrate and below the ground into the silicon substrate. So together, the continuous ground plane and the chessboard distribution of the structures are all expected to reduce the electromagnetic influence on the surroundings of the DOT. So let's use, once again, complete open as a validation structure for the comparison of run 1 and run 2. We note that both measured and probe simulated curves stick well to the intrinsic simulation, better in run 2 than run 1, which prove with this improved band-to-band continuity. And also we remark positive values of C12 at high frequency. This makes us confident of the better quality of our improved Run2 TRL cal kits. Where the curves deviate the most, however, is at the coupling capacitance, C12, that shows a non-physically negative behavior in the second band, which is the 140 to 120 gigahertz band. We have experienced this same discontinuous trend also after repeated measurements, and it is present in both fabrication runs, even in run 2 that is expected to reduce the probe to substrate coupling. But we have observed that this trend completely disappears if instead of pico probes we use one in the 140, 330 gigahertz band, we use the infinity probes. So we believe this is due, this behavior, non-physical behavior, is due to a port-to-port crosstalk specific to the set of probes, the pico probes, in this specific range, which is, as we know, not corrected by the TRL algorithm. So the following implementations, the following simulation sets are performed in order to conclude on whether R2 does reduce or not the impact of the surrounding. And if it does, we want to ask in which way. So we simulate two groups of DUT configurations, single isolated structures on a semi-infinite metal plane, which reduce the model complexity and the simulation times. While another set of simulation models consider the DUT with its adjacent structures, the neighbors, like in our real-world scenario. So both single and neighbor simulation have been altered in a later stage in order to add some R1 elements of the design into the R2 DUT models. The R2 backend of line with the ground on M1 is, however, maintained in all these simulations and in all these comparisons, so we cannot compare directly with run 1 measurements or simulation. So this analysis is carried out fully on the capacitance of the complete open that is once again used as a validation standard for the TRL. We compare simulations to run 2, both on intrinsic curves and measurements. So let's first take the single structure, and we add the 10 micrometer oxide ring around it. So the results are shown in the green curve. So the results are shown here in the green curve, and show that the port capacitance C11, but also C22, which is not shown, do not vary consistently. The coupling capacitance C12, on the other hand, tends to oscillate around the reference value at low as well as at the high frequency. And this is due to the newly formed crosstalk path inside the substrate. So if we move now to the simulation with neighbors, if we remove the chessboard configuration by aligning all the structures with the same reciprocal distances as in run 1, we obtain this cyan curve. So yes, so the cyan curve. C12 is almost unchanged, while an additional capacitance is present on C11 as a consequence of an increased coupling effect with the adjacent neighbors, which are those located just beneath the shadows of the probe. By also introducing the oxide ring, so we can see the purple curve to this configuration, we see on C12 the same kind of ripples as previously seen on the isolated structures, but we can also see an effect on the port capacitance now, as the purple curve is undulating more than before. So we think that this is due to the increased chances of coupling with neighbors that is allowed by the line configuration with green. Stray fields are in fact able to penetrate inside the silicon substrate and pervade the neighbors, as we can see in the electromagnetic simulation on the right here. On our run-to reference implementation, we can clearly see that our metallic continuous ground plane blocks completely the field, and its homogeneous topology makes easier to remove the coupling below the probe through calibration. So as a final electromagnetic simulation, we present this configuration which shows a 25% denser layout than the previous one. So no metallic ground plane separates the duties by its neighbors, unlike our continuous ground plane. This configuration is often used to save space and money on wafer fabrication. So it is interesting to see that in this case, the field uncontrollably scatters inside the substrate, and the structures are completely plunged into it. On the side view, we can also see a mode here below the structure that is the silicon substrate that is directly going below to the chuck. So let's move now to the innovative design part. So let's introduce the M3 lines. So as we said, in all transistor measurements, at least a complete open debedding must be performed after the TRL calibration to get the reference plane near the transistor pins. However, we have also pointed out that at extremely high frequencies, the dummies parameters, if they are not accurately described, may become frequency dependent, and moreover, errors increase when dummies are employed, since de-embedding actually compels to perform extra matrix calculations on the calibrated data. So one may try to get rid of this second part of the calibration. So in order to perform a one-tier or one-step calibration, we have implemented a different cal kit where the access lines are located at M3 level of the back-end line instead of M8. So in this scenario, we are much closer to the transistor, which is located below M1, and the reference plane, as a consequence, after the calibration, is therefore closer to the HBT in both vertical and horizontal direction, as we can see on the right. In this way, we remove a great portion of the possible back-end line parasitics. So due to the thinner M3 line cross-section, which provides a higher resistance, the losses on the line alpha are much higher and frequency dependent. A large part of the M3 line attenuation is removed after the TRL calibration, however. And we can also see that Z0, the characteristic impedance, is worse matched in this M3 implementation than the classic M8 implementation to the 50 ohm target. But both, I just recall that both Z0 values are corrected by our algorithm. So here we introduce the calibration flow and indicates the reference plane location for the next results. The first two scenarios in blue are the classic TRL. So the reference plane after the first step of calibration is set in two different locations for this first step. The reference location is defined by the TRL algorithm. So one location is close to the pads, as in the previous analysis on the previous slides, and is what we call the classic approach. And then the other position is close to the center of the through. That means closer to the HBT, but staying at M8. Then a standard complete short, complete open embedding is performed for both these classic approaches. The third scenario is the one-tier calibration target. So we take the measurements from the M3 versions of the backend of line of our transistor, and we perform M3 TRL, which is not followed by the embedding. The reference plane is therefore not exactly located at the same position as the two previous cases. In the final scenario, which aims simply to evaluate the M3 layout, we also perform the de-embedding, and we end up finally at the same position as the previous two cases, the cases in blue, but after an M3 TRL. So here are the results, which are shown on the maximum oscillation frequency, Fmax. So what we can see is that Fmax in the last band shows dips in both classic approaches, which we believe are due to the contact quality and wear pads, but this is not the only reason, and it will be I will clear this out later on. Then we can also see non-negligible noise on both M3 implementations that is linked to the inadequate power that we have injected into the transistor. Since, as we said, the lines are thinner and we have injected the same power as in the other bands, but due to the strong attenuation, the transistor received less power. We can also see in the first band losses that are linked to the M3 line on both these implementations, so after one-tier or two-tier calibration. And if we compare the classic approach to our target, which is the one-tier M3, we can see that there is an offset all along the frequency spectrum. And this means that actually the non-embedding method falls short in removing completely all the porosity contribution, and the bottleneck are the last metal stack elements, so M2 and M1, and particularly M1 and its how it is designed and its fingers. However, we can also notice that M3 with one-tier calibration is less noisy and better outlines all along the frequency spectrum, and this is due to the fact that we have no extra matrix computation after the calibration. So if now we compare the classic approach to the M3 after two-tier calibration, we can see that there is still an offset. They are not perfectly matched. So we have tried to figure out why this behavior is happening. And we have noticed that if we see the DC collector current inside the transistor for each of the frequency bands in each of the two implementations of the line, it is not constant and it varies. So what we try to do by IQM simulation and the retrieval of Fmax, we have first induced the observed variation on the collector current by changing the base emitter voltage, which is the input in the IQM model. Then we have also modeled a variation due to repeated contact by a delta on the extrinsic base resistance. And the value that we have chosen is 0.5 ohm, which is what we observed in real DC measurements. So in both cases, Fmax changes by approximately 10 gigahertz on average, and thus explaining perhaps the variation that we observed even with the same reference plane location. So now we move to the meander lines. The motivation is that another issue that we have tackled in our measuring campaigns is that the lines for TRL calibration have, of course, a different probe-to-probe distance compared to the other calibration standards and the HBT. So, for example, after measuring a calibration standard, one is forced to unzoom on the probing camera therefore losing his or her reference, in order to change the position of the probes to be able to adjust to the new line dimensions. So this probe displacement can be a problem and may generate measurements inaccuracy. So error linked to the discontinuous phase of S21 have also been observed due to this inaccurate probe alignment and repositioning. Even on one of the calibration standards, here we can see, for example, a line is shown here. So a possible solution is to create a new line topology which maintains the same pad-to-pad distance. So our solution, the meander line, is a modular solution. We take a unit cell of top-level copper that is routed by 45 degrees, and we join it together multiple times to create a sort of meandering pattern. So we create lines and through to work in the same frequency ranges as their straight counterparts. The lengths of these lines, however, they are not univocally defined. But if we see the imaginary part of the propagation constant, beta, this is easy to measure and is only dependent by theory on metal properties, on the material properties, sorry. So at a given frequency, beta should be the same for both straight and meander lines. By this observation and observing the well-known lengths of the straight lines, we have been able to calculate the effective meander lengths that are all reported on the table. So after applying the TRL calibration on the HPT and the 500 gigahertz line, with a straight line in one case and meander line on the other, we obtained the curves that are shown here, which are Fmax and the attenuation constant alpha. You clearly see that the trends with meander lines are consistent to the classic case in every region of the spectrum. In the final band, and particularly above 400 gigahertz, however, the curves deviate from the expected behavior, as you can see. The rise on the curves of Fmax, which is less significant for the straight case, but still present, is actually predicted by both simulation on the straight line and the meander line. And they replicate similar trends that are also seen on the lines alpha. So we have previously stated for the straight case that a bad contact or the wear of the RF pads could be the reason of this unexpected trend at extremely high frequencies. However, by looking closer to the parameters of the 500 gigahertz line, to find an explanation to this particular behavior, we have observed some dips on the reflection coefficient at wavelength value corresponding to the double of both straight and meander lines that hint to resonances on the lines, which become a half-wave resonator. We believe, in conclusion, that a calibration with such lines adds up, actually, errors in this last band. So we set up a simulation experiment, and we can see it here, to try and reduce the crosstalk by setting the axis of the meander lines and a modified version of the meander line, setting them apart and observe if the resonance persisted, and indeed it actually persisted, and it changed accordingly to the new lengths of the meander lines, the modified meander lines. So in conclusion, we can state that the new layout design improves calibration and limits the substrate modes by also reducing the interaction with the neighbors, thanks to the Chesper configuration. And the continuous ground plane actually avoids the fields to propagate inside the substrate and invade the other neighbors. As for the salt versus TRL analysis, we have seen actually very good results of the on-wafer salt. So that means that the lumped element models for the standards are quite good, up to extremely high frequencies. As for the M3 layouts, we have seen that one of the shortcomings is the non-negligible line losses. The HBT measurement without embedding, however, showed that they are less noisy, and this makes us confident about this technique. We think that paths covered or made of gold and a collector current control may solve some of the problems that we have seen with the inaccurate bias of our transistor. As for the meander line, a modular design actually allows a very similar accuracy with the classic straight lines as we have seen. But it is also imprecise in the last frequency band due to the resonances. So we propose one shorter meander line for covering the higher part of the spectrum. But we are still very confident about this layout, since it would prove very useful for example, automatic probing. And so if we see to the perspective now, run 2 is available, is here, and we are ready to measure it. It embeds 3 blocks. So some of the blocks we retake some of the previous calc kits, but we also add some structures to study the coupling, but also studying the crosstalk between the probes with this shifted pad configuration and this strip line-like implementation at M6. And we also have created some structures with an increased access line right for the study of the crosstalk, of the coupling, sorry. So here are some of the published work during this thesis. I would like to thank ST Microelectronics for providing the wafer, and this thesis has been partly co-founded by Taranto and Nano 2022. So thank you for your attention, and I will be pleased to answer to all your questions.
Okay, thank you very much, Marco, for this very nice presentation. So it's now time for questions. So I will first give the floor to your 2 reviewers, and we will begin with Christophe Caquier, from the professor from the University of Lille. So Christophe.
Thank you, Mr. Chairman, for your introduction. First of all, I'd like to... Do you hear me, first of all?
Yeah, I can hear you.
Okay, thanks. I'd like to thank Thomas to give me the opportunity to report on your thesis. It was very interesting. I have a few questions for sure. First of all, I would like to congratulate you for the quality of your presentation. The work done and the quality of the work and the quality of the presentation. This work called on a broad spectrum of skills to advance the understanding of this subject. This is important to stress that the accuracy of measurement of passive and active components is a real subject, knowing that the higher the frequency range, the greater the impact of error. For all that, this study is devoted to the impact of calibration kit and calibration methods used on the accuracy of measurement. Knowing that the future application, this millimeter and submillimeter wave frequency range will be used. So just the idea is just to underline that your study is perfectly in line with the working, let's say, the application who are coming. So I have a general question and some more specifics. One of the most important things from my part is you never speak about the contact resistance between the probe and the device under test, the repeatability of this contact and how you manage that, and did you see some impact when you, let's say, you have a degradation of the pad, because I assume you are making a lot of measurement, and so you need to have a good contact, and so it could also impact the accuracy of measurement. So Could you comment this aspect?
Yeah, we have made some study on the contact resistance varying after several contacts, and not me in particular, but during my campaign of measurements, we have done a study on the variation of the resistance of the contact. As I say in the presentation, it's the contact seems to be critical due to the contact on the aluminum pads, particularly in the final band. I have seen that the longer line we had, for example, multiple pose of the probes, and the results when using the probes that was wary actually degraded the final calibrated measurements of the transistor, for example. So we have observed this problem at high frequency. I suppose that at low frequency, below 110, the contact could be the reason for sometimes an offset with the intrinsic simulation that we see sometimes on the measurements. We have tried several contacts and several measurements on the 110 gigahertz band, but probably we deteriorated the pads. So yeah, I didn't put a study on the resistance of the contact, but it's something that can be done.
Okay, so it means for all the studies you have done and presented here, in order to have a good contact and to have a repeatability, you are just under bracket, let's say, but you just are working on the over travel. You don't measure the resistance of a contact.
We have also measured the resistance of the contact. We have checked it before every measurement. We have also tried to stay on let's say virgin structures. Every time we put the contact, we put the probes on novel structure to avoid the repeated pose.
Okay.
But we don't have a complete study after multiple probes of the multiple probe contacts of the degradation of the resistance, for example. This has not been done for the thesis, but we have the measurements, and we have checked every time that the resistance during the contact was something good.
Okay, thank you, Marco. I have a question regarding run one. In fact, I have two.
Yeah.
I don't understand why the ground plane, the first one, you have a ground plane which is composed of the metal 1 to metal 4 stack. What is the main reason for that?
I think that came from previous layouts and previous implementations, and we wanted to avoid that the field could penetrate inside the substrate, the silicon substrate. But since we have seen that no such thing was happening, we have decided finally to reduce on run 2 the thickness of the ground just to M1. I have also made some simulations to see if and when there was propagation inside the substrate. There was propagation, but I didn't see any changing by calibration in the final results. So I think that it is a good approach to just use M1 for ground.
Okay, because for the run 2 you put just M1. Usually in our labs we put M1 on M2. So from M1, from your point of view, is sufficient.
Yes, by simulation I have not seen any critical factor by using just M1. I mean, in terms of penetration of the field inside the substrate. I would also say that M1 does allows us to get closer, possibly, to the transistor by using, for example, the M3 line. So it is useful, and I don't have seen any bad results by using this. So.
Okay. And another small comment, and also we can exchange about that. For the run one, you try to have a very short length of through. It was 35 micron, if I well remember. So you underline this and saying, I want a short line because I want to have a very low losses. Okay, but in fact, when you are making the measurement, you don't have only the losses of the line, but you have the losses mainly also of the probes and these several dB. So I think to have a through, which is a very short line, from my point of view, is not very important. It's better to minimize the crosstalk. Sorry, the better is to minimize the crosstalk between the probes, even if you have, let's say, 0.5 or 0.6 dB more. What is your feeling about that?
I feel that it is true. We have increased a little bit the length of the through on the run-2 implementation, but I can say that still the crosstalk is a problem, and that is why in the next implementation of the run, and possibly I will do some measurements on that, we have decided to create structures just for studying the crosstalk, because we have seen that also by setting apart much more than the length of the through, even in run-2, we have experienced crosstalk. So it is something critical. It's not just the losses on the line, that is true.
Okay. Okay, perfect. And a question also regarding the back-end of line consideration. For the simulation, you replace all the, as you say, the complex stack with just a single block of silicon dioxide with a permittivity of around 4. From your point of view, which is the impact? Because I thought, in fact, you will use a 2 or 3 dielectric layer, but in your case, you just put, just once again on the bracket, because it's a, I will not say it's an easy simulation, but you just put one stack. Do you think it could have an impact? Did you try how you could justify to replace all this back end of line, let's say, with just one layer of silicon dioxide?
Actually, I'm not sure to understand, because I think that on run-2, I use, I'm pretty sure, positive, that I use 2 stacks of dielectric instead of 1, but let's say the general contribution is epsilon equal 4, more or less. So I use two different stacks to replicate the impact of the 30 stacks that are in the actual device. This is one of the first things I have done at the thesis, the evaluation of the impact of simplifying the electric stack by just 2. This simplification was done to make an harmonic average of all these 30 layers with just 2 elements, and I have double-checked that on the intrinsic device that this simplification was correct, and indeed I could get good results on both epsilon r, which is actually frequency dependent, and so in the lower part of the spectrum, epsilon r is a bit different, but the final value at high frequency is very similar to the complete stack. And I've also checked on the S21 parameters, for example, of the line and other structures. So this was checked at the very beginning of the thesis.
Okay, it's clear. Thanks. Now I'm moving to the characteristic impedance correction for TRL. So for that, you need to extract the propagation constant. And for that, this parameter is found by byproducts of a TRL calibration algorithm. And from my knowledge, this is usually extremely noisy.
Yeah.
And so I would like to have your comment regarding these points. What is the accuracy, and how you found? Do you think it's very interesting or not?
Do you think that it is not easy to extract gamma, or the? Is that
In
not?
fact, the extraction of gamma is very extremely noisy, from my point of view.
Yeah. So yeah, what I did for the so I use interpolated values of the C line, but also an interpolated value of beta. Beta, if I extract beta of the with the longer line, beta is actually quite constant, like quite. It has a good trend, linear trend. So the interpolation that I make, it does not change very significantly the results. However, as you can, as you had said, the alpha part, the losses, that measurement is it's a bit frequency dependent and is quite noisy, particularly if we move higher in frequency. And yeah, that is something that's very delicate to use. And I believe this is the cause of this behavior here on the fmax at low frequency, particularly. So I don't use an interpolation for alpha. I simply take the value of alpha that is provided by the lines, but I do take it. I mean, I cannot not use it, because otherwise the curves change a lot and they are not perfectly corrected. So yeah, it's not beta, it's alpha.
Okay.
Yeah.
Okay. I'm in line with that. Okay. In the chapter 3, you compare SALT and TRL calibration approach. It's the reference plane just after the pads. It's just to well in line what I'm speaking about. It was figure 3.38 in your thesis. It's just because I would like to speak a little bit about the inductances. So you underline that the on-wafer salt outperformed TRL in the while wool range for all the capacitance is perfectly right. So, but for the inductance, in fact, is not at all the case. And so I would like to have two comments. One is how you could explain this inductance is not in line, and what will be the impact on the measurement from your point of view?
So I agree. It is something that I've tried to figure better this out after the manuscript, and I could make some additional simulations. Actually, I took the same measurements. These are all measured results, and I did other data treatment. And so these results that are presented on the thesis use the pad open, pad short embedding after the calibration, the on-wafer calibration of the salt. So I believe that this trend on that you see in figure 337 is due to the embedding of the pad short embedding. I think that this is the case, because I also did some other data treatment with node embedding. I obtained these curves here. I don't know if you can see them.
Yeah.
So node embedding after the on-wafer salt on the inductances, and as you can see, if you have the thesis with you and you compare, the trends are much closer to the intrinsic line than the case of the manuscript. So I think that this extra embedding actually removes more than the intrinsic simulation, what is our reference plane with the intrinsic simulation. So they are more flat, but they do not stick with the intrinsic behavior. This is why.
Okay. Okay. Thanks a lot.
Thank you.
you have one or two more questions, and after I will stop because I don't want to take all the time. I'm moving to the chapter 4 when you are performing a one-tier calibration at metal 1. It's mainly on the figure 4.17, but I think you put also on the presentation, and you already gave some explanation. But honestly, I don't really understand. But perhaps I didn't. I missed something. It's where you have an important discrepancy between FT and even on Fmax at the low frequency. What I mean low frequency, or it's already relative, but it's, let's say, lower than 110.
Yeah. You mean, I think that you mean this, this trend here. Sorry, I try to, let's see. So this one.
Yes.
Okay. Yeah. This is something that came out. What I think is that when we do implement the impedance correction, actually we have to find Z0, and so Z0, if we recall the theory, is square root of R plus j omega L over G plus j omega C. So we suppose that we simplify this at high frequency to be just L over C, square root of L over C. However, since on this line, as I said, it's quite lossy, the resistance is higher, the R part of the equation still is there. So if this R part is there, there will be an imaginary part on Z0. We also, so this is one thing, and when we do the impedance correction, we take both the imaginary and real part of Z0. But as I said, I simplified the method, and the real part is just a constant value, while the imaginary part of Z0 is something that starts very negative value and then grows up and goes up to 0. So I believe that due to the fact that that we use the lump load method with this value, very simple value of the real part of Z0, it corrects corrects Z0 with our simplified value, but still the imaginary part of Z0 is present and changes the data after the calibration to replicate this steep trend, which is present on the expected measured value. So I don't know if I get to the point, but this is something that is due to the impedance correction, and it's due to the fact that we include alpha on the impedance correction, which is linked to the imaginary part of Z0, and so it modifies the calibrated data with a similar shape, with a similar steep trend as in the imaginary part of Z0. So I think that this part has to be more accurately explained. It's not a shortcoming of the impedance correction, I would say. It's something that, due to the simplification that we have made, could come up. But so yeah, I don't know if it's super clear.
Okay, I understand the spirit anyway. Okay, it's okay. I have one general question. So microstrip is a quasi-TEM at high frequency, as you underlined by and you present on some simulation. You can have other modes which could be excited. So you propose to use strip line, but do you think SCW, substrate integrated waveguide, could be also a solution?
Actually, CW.
You see what you see what
No,
is it?
not really. I don't catch it completely.
Okay. So don't. We will speak later on. So it's because it's more larger, let's say, question. So let's see. Yes, last question, and after we stop there, it was on the slide 39, because of course you answer already a lot of questions during the perspectives, but you claim lumped elements model find up to extremely high frequency. I'm waiting. Yeah.
Yeah, it's quite.
Oh, so it's yes, it was just the slide before. The slide, yes, here. It's for salt versus TRLs, because it's always a hot topic. What kind of calibration we have to use, salt. So, and here you say the lumped elements model, extremely high frequency. So, what do you mean by extremely high frequency?
That we have seen that the on-wafer salt works fine, I would say, up to 500 gigahertz. Also on the transistor, we see that it deviates on the final part. For example, on Fmax, starting from 400 gigahertz, but we cannot tell at this moment if it's due to the TRL and the line, the resonance, or to the on-wafer salt. But I mean the upper frequency band. So this is what I mean.
So upper, you mean up to 500?
Yes. If we see what we have found on the results, it could be used with without losing some too much precision up to this frequency.
Okay, so thank you, Marco, for the quality of the answer. Congratulations once again regarding the quality of the presentation, which was very pedagogic, and for the quality of the work, because you have covered widespread from EM simulation, design of elements, and the quality of measurement, because I know that do measurement at in this frequency range is not so easy, and it could take a lot of time. So congratulations once again.
Thank you. Thank you very much.
Thank you, Mr. President.
Okay, thank you, Christophe. So I will now give the floor to Marco Spirito, who is Associate Professor in TU Delft. So Marco. Marco, do you hear us?
It seems Marco is not connected. He is arriving, it seems.
Okay.
Can you hear me? Hello?
Yeah, I can hear you.
Okay. Yeah, no, I think there was a disconnection long before. Probably I had to be readmitted. Anyway, I followed everything. So thank you very much, Philippe, for the introduction and for inviting me. First of all, I also would like to actually acknowledge the really nice work that Marco did. As probably he knows, I also am fascinating a bit by this topic, and we do a lot of research that in my group, and I find it really interesting. So it really was a pleasure to read the thesis, which included a lot of effect from the calibration to the device characterization and design. So that has to be said. Of course, I'm here as a reviewer, and so now we will proceed to some questions. First of all, I want to dive into a bit the concept about crosstalk. I do feel that it is one of the hampering problems at this frequency, but I first want to kind of align a bit with you, because I think there was some differences in my view and what you were saying. So first of all, you introduce the problem of crosstalk, and I do believe that it's there, and even if you increase the distances with probe, it will not solve it. Yet you said something related to the fact that salt could correct easily for crosstalk, while TRL would not. Now, I will ask you a specific question. I mean, if we would do a crosstalk collection on a classical salt, do you know which kind of step of the measurement we tend to do?
What do you mean? Like, if we... I cannot get the question completely.
Okay, I believe that once you're talking about a salt with a correction, you're talking about the 12 error terms model. So yes, from a 10 error terms models, in order to extract what we tend to call XT and XT reverse, which type of measurement do we do?
Well, we took the coefficients of the standards that are used for the salt. We use the load, for example.
We actually use two loads at port 1 and port 2, and just we get the crosstalk, which is only going to be a frequency-dependent crosstalk. Now, that one, I think, is totally not capable of solving the problem that you have. And actually, if you would want from a TRL, which is an 8 error term model, you can convert it to a 10, and you could still add that step. So let's say that type of correction can be applied both in a salt environment as well as in a TRL. The real problem is that that one will not solve any problem, because probably you've also have seen it that the crosstalk is an impedance-dependent crosstalk. So an only frequency-dependent linkage between port 1 and port 2 will not solve anything. Now the question is, I think because you're also mentioning in your thesis, what do you think are the approaches we could take in order to overcome on this one? And what, at least from my point of view, well, I think there are many, but what are the drawbacks or why we are not using it?
Well, on the on-wafer salts, yes, indeed. I believe that if the on-wafer salt is not working exactly as it should, it's also due to the quality of the load that we employ, which is not a 50 ohm load. One of the approaches that we can do, and we actually do, is maybe an extra embedding step. So, for example,
we will gonna go in the details of the calibration standards in a second. If I would want to go above the problem of crosstalk, let's say that you guys are doing great job on simulation, they're gonna get even better. So we're gonna be perfectly simulating the standards, or the residual error of the cal kit is almost nothing, and we are only hampered by the crosstalk. What can I do to improve it?
I would say, well, I could say a posteriori, you can use some kind of correction with the help of simulation. I don't know. Otherwise.
But there is a technique that you also mentioned in your thesis that actually it's out there to correct for crosstalk.
Correct crosstalk.
Okay, I don't. Maybe you don't, but you mentioned it in your thesis. That's why I wanted to go there about the 16 error terms.
Yeah, can I recall at the moment? Could be.
Yeah. Well, the 16 error terms would actually handle that problem. My point is that you still become very much proposition dependent, and then we have an issue. But I think one of the nice things that you guys have presented is this meandered line in order to keep the distances constant. So in a sense, my point was there, yes, be careful also on trying to think how you're going to correct crosstalk, because crosstalk is going to be, I think, a problem that stays, and you'll have to think of solution. Now I'm hearing that you also have a third run that probably is going to bring you some more information. Okay, but let's say that we continue a bit propagating this part. Now, you mentioned also one thing related to the validity of terms, and then I would like you to be precise, because I didn't agree totally on one sentence you said during the presentation. You said that the embedding steps actually has a limitation, and it's related to frequency. And my question would be to you, can you be a bit more precise, because it's not only related to frequency?
Well, it is related to the fact that if we don't have if the quality of the de-embedding is not as we have modeled, we cannot completely treat the data, the calibrated data, in order to remove the extra parasitics.
Okay, let me rephrase the question. Is it only related to frequency or something else? Just to say, for example, if I would do a probe tip calibration and then I apply an open and short, or I do your M3 calibration, which is very close to the device, and I apply an open and short there, which one do you think is still very valid at 500 gigas?
I would say that open short.
Well, no, I'm talking about probe tip plus open and short, or M3 plus open and short?
Well, it also depends on the position of the reference plane and the backend of line.
In what cases we would like to have it at the intrinsic device plane, right? Because that's, I think, what the modeling guys want to have.
Yeah. So could be. I would say that both the approaches could be, since it's due to the de-embedding standards that we use, probably both approaches are going to be not exact, even though with the M3 line, with the M3 position, we can maybe better capture the behavior of the parasitics through the embedding step. So maybe I would say the M3.
I also would say that one, because I think the point that you want to make, and partially agree, is that it's not only the frequency, but also the amount of inductance and capacitance you have to remove.
Yeah.
So if you are at the probe tip, let's say, then the open and the short are large inductances. And that one cannot be captured, like you were saying, by an LC model, because it will have a self-resonance frequency. Now, once you go to M3, your residual inductance and capacitance becomes very small, and that allows you to push to higher frequencies. So it's not per se the step of an open and short that it's failing. It's if we are actually wanting to include the entire fixture in that model that is going to fail. That's why, I mean, if you have one atto farad and one femto Henry, trust me that thing will work up very easily to terahertz. So I think that is a bit of distinguish. Also, because one of the things that you said, it's that well, sometimes, and that is a question that I have to you precise. You said, well, we have that these parameters are not constant versus frequency. But is that actually something that we even do care about? I mean, in your modeling step, I think you subtract Y and Z matrices. You don't subtract L and C.
Yes, yes. It is not like we, as I said, as I show in the manuscript. Indeed, I make another on the validation structures. So the complete open and complete short. I go very much closer. By staying at the same metal 8 level, I go much closer, and I can see that indeed they are constant. So this is due to the parasitics that are along the lines that we do not remove in the step of the calibration if we stay close to the RF pads. Yeah, so this is we don't. We just want to check that the. Even though it is not constant, even it's changing with frequency, we just want to check that measurements and the simulation match with the.
Perfect. So I mean, my comment only there is that the fact that L1 or however you want to call it, it's fairly constant, is just to say, okay, that one is well capturing it. But if it changes 3%, that doesn't impact your accuracy, because you're actually going to use that frequency dependent value to subtract it. So the point is that it doesn't need to be perfectly constant. You just want to see that it's constant, that you can capture it in a single Y or Z element, but the Z or Y element can be frequency dependent.
Yes. Okay. I got it.
And then we agree, because that also links us a bit to the question that was said before related to the salt. Now, and I'm happy that you have the slides here. So here, we're saying lumped element models for standard work fine. And I'm also okay to say that, but does the salt really require a lumped element model? And don't think about what.
No, because it is like we cannot use frequency dependent values of the coefficients inside the salts algorithm. But yeah, we can use them, but you have to have good quality of them.
Yeah, but my point is that don't confuse of the way that Keysight is mapping the algorithm with the algorithm itself. C0, C1, C2, and C3 are just artifacts. The SALT algorithm uses gamma 1, gamma 2, and gamma 3. And gamma is a reflection coefficient frequency dependent. There is no need to map it to a lumped element equivalent. So that part, it only comes from the fact that that firmware most of the times were developed in 1970s, and they for legacy are not removing it. But the algorithm itself doesn't need it. So you, of course, need to have a good, accurate precision of that reflection coefficient, but it doesn't need to be a lumped model equivalent. That was my only point.
Yeah, and I think our implementation of the SALT is not, it's based on the lumped. So yeah, it's we use that algorithm, so we are compelled to extract at least the values.
Okay,
like
you can move away from that one, and because I think you're already showing, and also the previous reviewer was mentioning, you're already showing very good accuracy of the SALT up till high frequency, so that maybe can be a path to move forward. Now, I also have a question related, because you mentioned, I think, what was it, in slide 31, so probably a few slides before this one, that you had some limitation in power at higher frequency, and I can understand that the fixture as a power dependent, as a frequency dependent power loss, but yeah, you basically gave some of the fault to these more jumpy lines due to power. Then the question would come from a measurement standpoint: why didn't you level the power?
Well, because at that time we didn't think that it would be such a problem, and we do not concentrate, do not focus on the value of the power, the level of the power, but we rather use the same -30, -35 dBm for all the frequency ranges. Now that we know, definitely we will go with measurements more accurately.
So let me ask you, how do you set the -35? At which plane are you setting the -35?
We take the what is linked on the what is said on the output power that is written on the frequency extenders, and we go down up to a level that do not provoke distortion, but still is quite good to our experience to not have losses. And our experience was before this work in other bands, and at lower bands it was sufficient, -30, -35. So this is why.
Yeah, but you basically setting it through a power meter at the module head.
Yes, it's shown on the screen when you like we change the value mechanically, and it is reported on the display and on the screen, and we set
analyzer. But you're talking about the network. Okay, but then you do you do a source power calibration?
No, it's not done. No.
Okay. No, I understand. Okay, that's something that should be investigated. One other question is that you mentioned also this problem related to the current, and of course you're mentioning, which I think it's a logical step forward, to measure at constant current. But again, the question is, why wasn't those measurements done at constant current? What was the hampering fault there?
We have checked the currents on every measurements, but we could not provide the same exact value at each and every time. So we had the small differences. We did not think that this small difference could lead to bad behaviors, and indeed the measurements are quite good. But to explain this difference that we see in the curves, I have remarked that this delta that we see on the current could be biasing actually the transistor at a difference by a point. That is why. So the control would be would really improve this quality measurement, the measurement of the quality.
Okay, understood. One more point is that also on this figure, you mentioned that the discrepancy at lower frequency, one of the reasons was due to the alpha effect and its kind of impact at lower frequency. But I have another question is because I also think that you use fairly short lines in your TRL. What is the biggest line that you use?
It's 595 micron for up to 110 gigahertz. So
okay, now if we just look at the algorithm of the TRL and this 595 line, it's a line, right? And the through length is
95, 65
okay. So
actually, 65 without the axes. Yeah.
So the lambda, the line excess length is 500 micron, right? Because it's all, we always have to compare it to the true length. Now, according to the TRL algorithms, when is it going to fail in terms of the electrical length of the line? There is a kind of description of the line length that we use in order to say, well, it's going to be accurate when the distances between the line and the true is how much?
Yeah, it should be not exceed the lambda over 4. So the electrical the degree should be between 20 and 160 degrees of difference between the two.
And why is that?
Because otherwise the behavior of the line will be very similar to that of the true.
Perfect. Now, according to you, when we go below to 30 gigahertz, is your line still above the 20 degrees compared to the true?
No, that is, well, 30, 20, that is why we remove the lower part of the spectrum, because the validity starts at 20. We have calculated it with a simplified form that you find in the manuscript, but still it's based on the idea that you have to stay between the 20 and 160 degrees.
Okay, a very good explanation. I'm really liking it. That is my point. I wanted to impact, since Fmax always expands tremendously every error of the S parameters, my guess is when you're starting to go below 50 gigahertz, of course, strictly speaking, the 20 degrees you're above, but your error is start to increase. And that's why you have an expansion of that error there. I think that is could be even more than your alpha that you described, which could still be the case.
Yeah.
One extra question, because I'm always fascinating. I think that the TRL is a beautiful algorithms, but it really relies a lot on Z0. And I understood that you worked a lot with the kind of the approaches from Dylan Williams, and you also added the alpha. But now I have one question is, how much do you think the fact that you have a non-uniform line impacts that algorithm?
You mean a non-uniform line on the for
considering that even if you consider your straight line, your line has pads, and then the line is thinner than the pads.
Of course. Okay.
How do you handle that?
Well, first of all, we try to put the reference plane far away from the pads. So
sorry to interrupt you. I just want to know related to the Z0. I understand that your cal is done properly because you put the reference plane away, but for the Z0 extraction.
Yes, yeah, there is actually for the Z0 extraction, we perform the calibration. We set ourselves at our desired reference plane, and we use that value for extracting the reflection coefficients of the load. So when we use the load, we are actually we have already calibrated the transition. So I don't think that it.
But then you're using the model of the load.
No, I use measurements.
Okay, but then but your load is a load embedded in the silicon.
Yes.
So you still need to have a simulation package of that load.
Yes, to account
for all the parasitics around it.
Well, actually, we take the load part, the S parameters of the load. We take them from measurements as well. But the load
those measurements are still not normalized to 50 ohm because you still didn't apply the.
Yes, they are calibrated but not normalized.
Okay, so then again, how do you know the value of the load in order to extract the characteristic impedance of the line?
We have found it to be 36 ohm, more or less by simulation, yes. And we have double checked after implementing our method with the measured value.
Okay, so if I understand correctly, you basically do a DC measurement on the load. You get its DC value. You check that it maps with your simulation, and then you're using that reflection coefficient at that plane, and from that you extract Z0.
Yes, that value, yeah.
Okay, okay. Yeah, I always think that in the Z0 extraction, it's always very tricky with the when a pad is there because you don't have an independent way. But I understand now the method that you did. Thanks for explaining. One more thing is that the meander line, I find it a very nice solution, and of course, I won't hide the fact that at the beginning I always was thinking that a meander line cannot really work. But if we look at your data, I think it's very promising. But from an electromagnetic standpoint, and you're showing somewhat in the last slides, what is the fact that the meander line should cause problem? If you just explain me, like I'm an EM student, what is the key thing of a meander line that intrinsically should not make it work? Apart from, we're seeing, like you were mentioning on reference one, that really the closeness of these two lines might introduce a capacitance. So you might really have an LC kind of resonator there. But if I just go on the basics, why a lot of us don't like to use meander line?
Possibly because of the angles on the line that could possibly put create some reflections on the wave that is propagating, and also, yeah, I would say this, and the fact that the coupling could be non-negligible and could have some results on calibration, but we see that this is not really what impacts the most the calibrated measurements.
Yeah, because always when I see a meander line, I always imagine that at every of this band, even if little, you have a discontinuity, right? And in a discontinuity, you can excite other modes, because your line also, as it was mentioned before, it's quasi TM, but does supports other modes. So my question is, how do you enforce here that you're canceling all the possible other modes and you're only maintaining it? I think you're using a pseudo microstrip type of mode.
We have performed simulation, and we, like in the straight case, and we did not find the modes to increase a lot over frequency. But yes, as I said, at the angles could be there could be some generation of reflection of the wave, so generation of other modes, higher order modes, and but we didn't see on intrinsic simulation. This was also one of the possibilities to explain this increase at high frequency at the beginning. But after simulation and after seeing that the resonance is more consistent with the final results, I think that higher order mode propagation is not really could not impact as much, let's say, the final results of the measurements. Maybe there is, but it's not impacting a lot the results.
Okay, and in lines such like this, what would be the strategy that you would use for the Z0 extraction?
For the Z0 extraction, well, actually, the definition of the effective length is based on beta, and then beta is along with gamma is used for the extraction of Z0. What I did here is to use the same kind of Z0 extraction as in the other measurements.
So you would use the load for a meander, or you would use the load of a straight and then just apply the same Z at 0 here?
Yeah, this is a good point, because we have the load of the straights, which is not implemented for the meander structure. We do have we have to for a rigorous procedure, we should implement also a load that is located in the middle of the meander through, which is not the case at the moment. And yeah, this is a good point. Yeah, it should be done.
Okay. Well, I think I asked a lot. Sorry, I was interrupting you a lot while you were asking, just out of curiosity. But
Yeah.
I can say to the president, Philippe, I'm satisfied with my Q&A session.
Okay, thank you, Marco. So now I will give the floor to the two other members of the jury who are connected remotely. So first of all, I will ask Chandan Yadav, who is Associate Professor at the National Institute of Technology in Calicut in India. So please, Chandan.
Thank you very much, Mr. President, to invite me for the question. Thank you very much, Marco, for this nice presentation, having a high quality work. I would like to thank Professor Thomas, Marina, and Sebastian for giving me opportunity to be part of your thesis presentation. I would like to ask very few questions because in past I had many opportunities to ask you many questions and have had many interactions with you related to your work. One question is related to the substrate mode, like in the new layout structures, like you have mentioned that they are limiting the substrate mode compared to the old layout structure. So what is the reason behind this?
The reason behind the substrate mode that is not present, you mean?
In new layout structures.
Yeah, what we believe is that due to the fact that the opening, the holes inside the ground plane are much smaller and fewer than the case of a structure with slots like the oxide ring, the field is not able to penetrate inside the silicon substrate in order to form some parasitic modes. So I think that this is due to the continuous ground plane that blocks the propagation inside the substrate. Yeah.
Okay. One question is like related to the on-wafer salt. Like if I look into your thesis on page number 75, then I can see that if you are measuring transistor open and applying it using for transistor open in the measurement, then I can see that on-wafer salt is like giving like better measurement results. But if I look into like results of the transistor sort, then I can see that for the inductance, like TRL is better, like TRL is predicting results that are very close to intrinsic compared to the on-wafer salt.
Yeah. I think I partly answered to this previously, because this is due, in my opinion, to the de-embedding step that we provide after the on-wafer salt. And since it's a pad open, pad short de-embedding also for the passive, we can see that in fact it's flatter, and it's way different from the frequency dependent behavior that we have by simulation and with the TRL. And if you look at this, this is without the embedding. And since we have not removed the additional inductance, well, we have very similar results as like in the TRI.
Okay.
Yeah.
Okay. Thank you very much, Marco. Thank you, Mr. President. I had only these questions.
Okay, thank you, Mr. Yadav. So I will now give the floor to Cédric Durand, who is a doctor engineer in ST Microelectronics in Kroll. So please, Cédric.
So, okay, can you hear me?
Yeah, I can hear you.
Okay, so thanks, Mr. President. Thank you, Marco, for this very nice presentation and very nice topic. And also thanks to Sébastien, Marina, and Thomas to invite me for this defense. As I'm an ST representative here, it's always a pleasure to see that people are using ST technologies, and in particular here concerning the topic of extraction of devices. As you know, for ST, it's very important to be able to demonstrate to our customers by measurements that the devices we put in the technologies have the performances that are expected and proposed in the models. So it's a very nice to try to measure the performance of HBT at the level of the device and not at the level of a design. So in terms of questions, I will maybe concentrate on some questions regarding industrial aspects. So if you go to slide number 34, please.
Yes.
You speak in this slide. There is some. Sorry, my phone is moving. So on this slide, you see that there is a meander approach, and you say that it was a solution to avoid probes moving. If now we consider, let's say, an industrial full automatic tester as it's available at ST, for example, and if we consider that the precision of probe positioning is, let's say, 1 micron, and that we can also change the positioner position automatically, do you think meander line is still of interest?
I would say yes, because you definitely can handle just by removing the probes and setting them back on the substrate and changing the position of the wafer. You can set multiple measurements even without moving one of the probes. We have seen that also moving the probes and the cables and so on could propagate some errors on the measurements. So maybe there are smaller errors. We don't have a complete study on this, but there could be some errors due to the fact that one of the probe is moving, or both of the probes are moving in one of the direction. But yes, I'm definitely positive that you can use this kind of meander line that has some interest for even automatic probing. That is definitely the case. Of course, also for manual probing, but yes, it would speed up and reduce the error, I think.
Okay, and so if you in terms of meander lines, so if you go to the conclusion, you say that it's suitable for automatic probing. So you mean by automatic probing that you do not change the distance in between probes, right?
Yes. Yes.
Okay, and for that, what do you think in terms of perspective on slide 40? If we consider also an automatic prober, do you think what is the most interesting to do in between shifted pads, meander lines, or automatic move of the probe distance? What would be your
Yeah, I think that actually the shifted pads tackle another problem and are made for our purpose of studying the crosstalk influence between the probes. Indeed, if you put the probes into different position and observe the crosstalk should be reduced. So we can imagine that, yeah. I'd say that meander line is dedicated to this aspect and would provide good results if it's used. For shifted pads, I don't know. Could be also a possibility since the pads are actually closer, but you still have to move in the other direction. So you still have a movement. But if all the elements of the calc kit are implemented in the same way, yeah. The fact is that with actually the shifted pad that does not remove this problem. I mean, the line is still there, as you can see. It's not the pads are change their position. If you can see, well, in the manuscript you can see it, but here there's the 100 gigahertz shifted pad line, and as you can see, it's long, and the probes should be very distanced. So you don't solve that. You cannot solve that problem with this, but with the meander line, yes, you do. I think you can do automatic probing.
Okay, thanks. And maybe now a question concerning the page 74 of the manuscripts. It's when you compare on 500 length transmission line or through the S21 between on wafer salt on ISS, and also TRL, etc. As you explained, there is a bump, let's say, on the ISS salt. Could you please come back on the explanation of this bump on your point of view?
Can you tell me the number of the picture?
74 picture 3.36.
Okay. So here, here we use the meander line as a validation standard, and we use the classic TRL calibration kit. So you can see that the on-wafer salt proves quite good. Replicates very good the meander, the magnitude of S12, while also doing the same good behavior with the phase of S12, but with a higher offset compared to the simulation. So yeah, in fact, basically you have the TRL where you take the all the passive raw data. You apply the TRL plus the impedance correction. And
the precise question is, let's say, consider above 110 gigs. Yes. Yeah, there is a bump, and this bump is removed from salt on ISS to on wafer salt, right?
Yes.
And to what you attribute this bump? Is it the fact that you make the salt on ISS and then go to silicon, so it's coupling from ISS to silicon that is different, or is it more related to what Marco said, to a limitation of the description of by lumped components C0, L0, etc. of the ISS standard, for example?
The bump there, could be linked to the definitely could be linked to the lumped element description, which is a shortcoming, but maybe it's also due to the quality of the extracted parameters, the coefficient for the salts. Yes, it could be related.
For example, if you maybe describe ISS standards better than only by lumped elements, do you think it would be we will be able to remove this bump, or do you think it's more linked to the fact we make the calibration on one substrate and then measure on another one?
I think that at this frequency, maybe you can improve it with the just with the better description of the standards. I'm not sure. I should look at this. But I mean, like in this work, we had not very good results on the ISS, independently of the fact that it's on another substrate. Could be, yeah. I agree with you that there is a huge difference, which I've not experienced in other measurements with ISS as well. So I cannot tell definitely.
Okay.
What's the reason? Yeah.
So maybe also a question related to let's say you only show let's say one measurement on each graph. I don't know if you made some statistics measurement. If no, we consider, for example, we want to measure 50 or 100 of HBT in a DOE. What do you think would be the most suitable calibration method? Do you think if we measure 50 devices, we need to, for example, for salt, to make the calibration only one time, or for each device? What do you think of how we can maybe deal with lots of measurement and only not one device measurement with this calibration methods? And what would be the most appropriate to industrial measurements? I mean, several measurements, 50 or more.
Well, I would say that the TRL, what we did is to use for each measurement on the transistor, give at the same time, just before, a measurement on the standards. And we have also experienced that this the calibration could not be stable for a long time, so we had to repeat the cal in order to make it stable. Between these two methods, probably the TRL measurements could stay. We can reuse the TRL measurement for multiple other measurements of the device under test. I don't know, but it is not something that we do 50 measurements on the same device. It's Here we tend to concentrate on the quality of the measurement, and we take a calibration just before every time to make sure that it's not diverging from what we are going to measure next.
Okay, it was just to have an idea of, let's say, industrialized perspectives of your work. So, and last maybe a question or comment. You will you say in the perspectives that one of the aim is to make the modelization, EM modelization of other probes. So it seems that the aim is to model every probe that can be used. Don't you think maybe in the long term it would be better to go out from probes modeling and try to find a way to de-embed probe effects? Do you have a perspective on that?
Well, I think that the two things go hand in hand. I mean, if we are trying to make models of the probe because like for example, in the 140 to 120 gigahertz, we saw that the measurement was not physical at all. But we have also seen that simulation was replicating that aspect. And so we have seen this by using the probe, the model of the probe, and this was essential to understand that this was the reason and not the other. And other probes are expected to behave slightly better, like the infinity probe in that region, for example. So in order to remove all these parasitics linked to the probes, I think that it's needed to have a complete model of the tips. I think that during this work, having a model of the tip really helped to improve the quality and find the quality of the measurements, and also find an explanation for a lot of things.
Okay, so thank you. I will stop there. So again, thanks for this this subject, this presentation that is very interesting and very hard topic and pluridisciplinary topic. And thanks for that. So I'll give back the talk to the president. Thank you.
Okay, thank you, Cédric. So before to give the floor to the three supervisors, we will ask some questions. So first of all, I want to thank Marina, Thomas, and Sebastian for the invitation to attend the defense of Marco today concerning a very interesting work, the problem of calibration and measurement at very high frequency, which is an open subject, an open topics for sure. And as underlined by all the other jury members, the work carried out by Marco is very impressive, with like a pluridisciplinary topics as underlined by Cédric just before. And also I would like to congratulate you for the very nice presentation.
Thank you.
The talk given today. So I will ask only two questions because I had a lot of questions, but the reviewers and Cédric also already asked the question. But I have two questions remaining. First of all, you say that it's preferable to use a complete ground around the devices. But what about the DRC rules?
Yeah.
Case?
Yeah. Yes. This is actually we could do because of the DRC rules allowed us to do it, but it's something that we have to consider. So, like for example, the fact here. This is another thing, but just to say that the DRC rule are
Sorry, Marco, did you by chance unmute? Because I can't hear anything anymore. This is Marco Spirito talking.
Yeah,
Oh,
I'm not unmuting. I didn't touch anything.
now it's back. Now it's back the audio. Thanks.
Okay. Yeah, this was done on the Run One layout, and I hadn't checked personally the if this was happening. It is supposed to come in the next week because I'm going to really set on the simulation for all this Run 3 implementation, and then we will see if it's there. But I've seen the simulations at the beginning on this M6, and we did not see we have implemented actually to have good agreement with the simulation that we already have. But
yes, but what I mean is that if you use strip line, you have to reduce the width of the strip
yes.
for the same characteristic impedance.
Yes.
So what did you study the impact in terms of insertion loss?
I don't think it was done at the moment.
And did you try also to use a cap instead of metal 8?
I think that it's not possible due to the rules on this. Yeah, due to the rules, it's not possible. But no, we hadn't tried. I know that other works on MOS, they use the alucap as the top metal, but not here.
Okay, thanks again, Marco, for the nice presentation. Now I will give the floor to the three supervisor. I will begin with Marina. Marina.
Thank you, Mr. President. First of all, congratulations, Marco, for this very nice presentation. You did a very great job there. Yeah, your PhD, yeah, it's very similar to the PhD work we have done with us during these 3 last years. And as my first PhD student, it was a really great pleasure to be one of the supervisors. And you really have many qualities as a young professional, being very committed and efficient, as well as human qualities. And I really want to underline this.
Thank you.
I really enjoyed to go to your first conference in the United States. I wish you a great future on all your projects. And I'm very happy to continue to work on this topic with you for your postdoc for the upcoming years.
Thank you, Marina. Thank you.
Okay, thank you, Marina. So now it's time to give the floor to Sebastian.
Thank you, Mr. President. So Marco, your presentation was really nice, and it has been always the case. I have to say, all the presentations that you have done are always of good quality, very good quality. So, and also I have to say that you are a student that doesn't need so much help for writing your paper. Comes just need when it comes just need a small polishing of the paper. That's really a good thing for supervisors. I have to say also that when you arrive at the beginning, I remember you take your course and you read everything, your master course, and to learn all these things and to verify all the theory that for the lines. And I remember that you have carefully verified the approximation on the back end of line. It comes to the question of Christophe Gaquier. I remember that we made all this stack of layers, of dielectric layers, and you compare with and without, with a simplified dielectric. You also implemented the dummies to see the effects. All these things maybe were not in the thesis, but you have made all these verifications. And you wanted to be always very accurate. And this last year, you have been also very autonomous. We just made your work, propose new things, For example, the salt on wafer, you made it by your own. You made it. Most of the thing maybe with a little help, but the new ideas come from you. That was a great thing. What I have to say, maybe I should maybe try to make a few comments on the comments from Christophe and many from Christophe. So about the contact, we are working on. We are always verifying the resistance of a screw or line or short. But we also now we have started a new study with Thomas and with the team about we are comparing pad with gold and pad with aluminum, and we compare different probes. And we have seen that very thin probes, which with 50 micrometer pitch, are much more sensitive to. And on aluminum, we have the contact is not so reliable, while on gold it's very nice. About I can also say that crosstalk, of course, is a really important problem. We have seen it, and we have seen that it is also probe geometry dependent. And this is maybe an important work to do for your postdoc. About the power control in the thesis, it was not the power control at the extender. It was not done during the thesis, but now we have electronic power control. So it will be also done in the next years. And about the sort of wafers, I think there is still some work to do. We talked about this 2 days ago. Okay, that's it, and I would like to thank you again for these 3 years. It's really a good thing for me, a good thing, a good relation between. I appreciate your work.
Thank
you.
Okay, thank you, Sebastian. So I give the floor to Thomas, the last.
Okay, thank you, Mr. President. I take my sheet of paper. When we started the defense today, so it took some time to settle up everything. And as it was said already, it was like a thesis. At the very beginning, it took some time to set up your thesis. And this is not because you didn't understand it. It was because the thesis subject was or is so extremely complex. It's not trivial at all. This is I want to congratulate you for 3 things. First of all, for all the measurements you did. You showed tons of results in your thesis. So many results. Each measurement curve up to 500 gigahertz. That means you did 4 measurements each time. And all the people who are doing measurements, they know how difficult it is, and it's not just 1 measurement that has been done. There are 10 measurements that has been done to double check everything, putting everything together. Yeah. This is really, I want to congratulate you for this huge amount of work that you did. It is really incredible. And the results are really, really so impressive. We can discuss a lot of curves still for next 10 years that you gave us so many research. So that's the first point. The second point where I want to congratulate you is to manage to use this electromagnetic simulation tool, because here you have a measurement instrument. You will always get S parameters, but you never know what about the S parameters. Are these something that is good or is not good? They're looking strange. Why are you looking strange? No clue. We need some tool. And again, congratulations for that, because making this complex electromagnetic simulation, this simulation, the probe tip simulations, the standards, making the TRL with the simulation and all this stuff, takes so long to make all this simulation. Hours and days for 1 simulation. And again, we have we have to do it for each frequency band. You have to do it and you change into probe tips, you start again, and there was something wrong, and you start again, and you made that there was one parameter not correct, and you start a third time, and so on and so on. Again, congratulations for all this huge work on the simulation. And finally, once you mastered everything, then you came up with new ideas for the best structures. We presented some of them down the line times 3. New ideas how to treat the data, solve, changing the procedure, investigating the impedance. So again, all the spectrum that you covered with new ideas, congratulations for that. And finally, for this, I want to thank you for also, because not only you did a lot of research work, you were also very helpful for teaching. I asked you to help us because we had some problems. We were looking for people helping us. Colleagues of mine were not available for teaching, and you say, okay, I will do it from today for tomorrow. Just immediately you were available, you made you available. And this is also in this very difficult times we are living now with the students and so on. I want to thank you for that. And I can tell you the students appreciate you very, very well. So, this being said, I have one question. Next slide, please. So, but the question is easy. You can say yes or no. The question is, do you have some ideas for the run number 4?
Yes. Yes.
That's all I want to know. So keep it.
Okay, we will discuss. We'll discuss.
Mr. President.
Okay, so now the jury will talk and we'll come back in 15 minutes or less.
Okay.
It definitely changes your life. It helps you establish relationships that are really tighter because you already have a lot of things in common in the way you think, work, want to change the world around you.
As you get involved in IEEE, you really get a sense that you want to give back and to grow the community that you have.
I think there's a natural intersection between IEEE and its role in promoting the emergence of new technologies and entrepreneurship.
IEEE was a great channel to get to connect with professionals in the field. You never know what's going to happen when you meet so prominent people that are foreseeing the future.
What has IEEE brought me? I've worked full-time in power system automation, which we call smart grid, for over 41 years now, full-time. And the job changes I've made were through industry friends that knew of opportunities that I wouldn't have known otherwise and open up the door for me. And many of these industry friends I met through IEEE.
What other place can you try to take a risk of doing our presentation skills and bringing in somebody from industry to talk to other scientists and engineers? I've been a member of IEEE for 25 years, and I still talk and mentor about this to this day.
IEEE has given me opportunities to network in terms of getting to know the leaders in the field, and also has provided an outlet for those leaders to know what I'm doing. So it's been good for both of us.
Given the world that we're living in now, where everything is pretty much about the internet and about connectivity, it's actually a good time to be an engineer and to be a telecommunications and networking engineer.
We know it's about the dynamics between people and people groups where our future is. And engineers can facilitate that, but they don't have the answers. It's the answering of us together as a community, not as engineers alone. So engineering is not going to solve the world, but it's going to facilitate that problem solving and getting together.
At IEEE, we believe technologists are the key drivers of tomorrow's innovations because we can really do what IEEE's motto states. We can advance technology for the benefit of humanity.
I always wanted my education to mean something more than just, doing a day job that pays my checks.
I wanted to see how my background in engineering and other things could have an impact that can make somebody's life better.
Being able to connect our members with younger students and engaging them to emphasize that it is important, that what they are pursuing in their STEM careers is truly going to be the next thing that affects all of humanity, because all technology that we make is affecting people, and it's not just IEEE members, it's everybody.
Marco, we have no sound.
Everybody can hear you.
Yeah, it's okay.
Good.
So, we have discussed the presentation of the thesis inside the jury. So the jury want to congratulate you for the quality of the presentation that confirmed the quality of the work. You're understanding all the topics you work on, which are in line with the needs for future applications. So it's linked to industry, with the environment of ST microelectronics. You did a very wide work, spread it into EM simulation, layout, measurements. The presentation was very pedagogical, and you gave a very good description of all the action you have done during the work. You also answered with a very good quality to all the questions asked by the members of the jury on a complex subject. So for all these reasons, the jury give you the title of Doctor of the University of Bordeaux. Congratulations.
Thank you. Thank you.
Congratulations.
So thank you everybody. Well, I wanted to thank, first of all, Professor Ferrari to come here today, even though this situation is quite complex, complicated, and to have taken a flight here, and all the committee members to have joined and read the manuscript. Thank you for your feedback. It was really helpful, and I would like to thank you, my supervisors, but since I'm not as good at talking as for thanking, as I am quite confident when I talk like this. I wrote something and I wanted to thank you. So first of all, I wanted to thank Thomas, but je parle en français parce que ça me fait toujours bizarre de vous parler à mes encadrants en anglais. Je te remercie Thomas parce que tu étais un peu la référence, tu étais un peu la personne à qui s'adresser pour chercher la réponse, pour trancher sur une question, pour savoir un peu où aller dans la recherche. Et mais aussi en plus de ça, tu as toujours su établir un très bon équilibre, je trouve, entre la recherche et l'écoute personnelle. Donc c'est vraiment ça fait tout d'une thèse, je trouve. Donc merci. Et après je tiens à remercier Sébastien parce que c'est la personne avec qui je travaille depuis plus longtemps, je pense. Ça fait 4 ans. D'abord c'était l'Erasmus, après du coup maintenant la thèse. Ça va être le postdoc. Du coup c'est vraiment beaucoup. Et toi aussi, à chaque fois que toutes mes conventions étaient un peu ébranlées, je savais que je pouvais te demander, avoir un petit retour. Et tu as toujours eu la patience de répondre. Et tu as su toujours lever mes doutes. Et c'est vraiment enrichissant du point de vue professionnel, mais aussi personnel. Et je te remercie aussi pour toutes les campagnes de mesures qu'on a fait. On a passé des mois et des mois en salle de Carac. Et du coup, je remercie aussi Magali pour nous avoir aidés. C'était vraiment long. Et enfin, je vais remercier Marina qui m'a accompagné dès le début. Elle était toujours disponible à l'écoute, vraiment, de tout ce que je ressentais. Et elle a toujours cru en mes capacités. Elle m'a toujours beaucoup poussé et engagé dans ce que je faisais. Et je tiens aussi à te dire que j'ai un très bon souvenir de la conférence aux États-Unis aussi. C'est vraiment un des plus beaux souvenirs de ces 3 années. Et puis bon, je remercie tous les autres doctorants de la salle, ceux qui sont déjà partis ailleurs, Djeber, Jean-Charles pour gérer la connexion et tout. Et je remercie aussi Déborah qui c'était une drôle d'année et elle était toujours à côté, elle m'a beaucoup aidé. Et je sais que c'était pas facile, surtout cette dernière période. Pour toi aussi, mais bon. On y est arrivé. Et voilà, je remercie tous mes amis que peut-être ils me regardent maintenant en streaming ou plus tard, je sais pas. Et du coup, je voulais dire un truc en italien parce que du coup, je pense qu'il y a ma mère, toute la famille qui me regarde. Du coup, ringrazio mamma, nonna, papà, gli zii, cugini, tutti quanti, se mi state guardando, non lo so. Grazie perché anche lo so che magari non è sempre stato facile accettare e anche adattarsi al fatto che sia lontano mi ha dato delle belle soddisfazioni e sono felice, quindi grazie e ringrazio anche i miei amici se mi stanno guardando in questo momento. Voilà, c'est tout.
Merci.
Bon, merci à tous. Merci. Voilà.
Donc nous le 5 on va manger ensemble maintenant.
Ok, ça marche.
À la bibliothèque.
Ok. Je débarrasse tout ça, j'accompagne Déborah à la porte.
So